Hello, I'm Hyung Park. I will explain about nitrogen vacancy center in diamond, which is used in single photon emitter. First, let me talk about introduce. In 1982, Richard Feynman suggested about the quantum mechanical system could be used to simulate and calculate. It is the start of quantum computing. Since then, theoretical study about quantum computing was carried out over the next 10 years, and quantum teleportation and quantum cryptography were developed. The fundamental ingredients needed to make quantum cryptography work, single photon emitters, is discussed. The ideal single photon emitter needed for quantum cryptography should emit no more than one photon at a time. Also, for practical use, they should be easy to create, easy to control, be fast, and should work at room temperature. MB centers are components that satisfy these conditions and have a property of photoluminescence, which can be easily detected from an individual MB center, especially those in the negative charge state. By these reasons, much attention in quantum optics has been paid to the study of single nitrogen vacancy detect center in diamond in recent years. Now, let's look over MB center in diamond more deeper. First is the MB center structure. A nitrogen vacancy center is a point detected in the diamond lattice. It consists of a nearest neighbor pair of the nitrogen atom, which is substituted for a carbon atom, and a lattice vacancy. A nitrogen atom has 5 valence electrons. 3 of them covalently bond to the carbon atoms, and 2 remain non-bonded. Therefore, compared to a perfect diamond crystal, the number of electrons that do not participate in the formulation of covalent bond is 1 from a nitrogen atom and 4 from a vacancy. Therefore, 5 electrons exist in the vicinity of an electrically neutral MB center. However, such an MB center can capture an extra electrons from somewhere in the lattice and from a singly negative MB center. In this case, 2 electrons from a spin triplet state. The triplet state is a quantum state in which the electron spins can exist in the same state, resulting in 4 possible states, and thus the MS can be presented as -1, 1, 0. We have confirmed that the structure of the MB center creates a triplet state. We will now take a closer look at the energy state of the MB center. This is the energy state of the MB- center of diamond. 1A is metastable state, and 3A is ground state. 3E is excited state. The number 3 in 3A and 1 in 1A represent the number of allowable MS spin states. In the absence of an external magnetic field, the ground and excited state are split by magnetic interaction between the 2 unpaired electrons at the MB- center. When 2 electrons have parallel spins, their energy is higher than when spins are antiparallel. It is about 2.87 GHz above. The electronic states are mediated by a photon which cannot change over spin. Thus, optical transitions must preserve the total spin and occur between levels of the same total spin. By transition, a red fluorescent light of 637 nanometer will be emitted, and we can read our spin state via fluorescence in near-infrared range. This is related with non-radiative transition between 3E and 1A. It is stronger for MS is ±1 and weaker for MS is 0. Spin state with MS is 0 due to conservation of spin in transition. It will be excited to the corresponding MS is 0 state in 3 and then go back to the original state. However, for a spin state with MS is ±1 in 3A, after the excitation, it has the relatively high probability to jump to the intermediate state 1A by non-radiative transition and go to the ground state with MS is 0. That is when the spin is excited to the MS is plus minus 1 level, the read-write output of the detect is reduced slightly, and it is providing a means for detecting the spin state by monitoring changes in the photoluminescence. Furthermore, the energy level of the MS is plus minus 1 states are tunable with extra magnetic field. This is called a Zeeman effect, which is the effect of splitting for a spectral line into several components in the presence of a static magnetic field. Therefore, the intensity and position of the luminescence line can be modulated by applying electronic or and magnetic field. As well as MB center have a property of photoluminescence by the energy state, the electrons of the dangling bond at the MB site hybridize to produce long spin lifetimes and well-defined energy state, even at room temperature. So the MB center is considered an important component as a single photon emitter. This is the reference. Thanks for watching.